Hello, welcome to the lecture for Wednesday, 3/18/2020. I'm actually recording this the day before on St. Patty's Day, so happy St. Patty's Day belated, or you might see this today, so happy St. Patty's Day. And remember, when you're watching these videos, when you get to problems, pause. There's Sky's paw, she's so cute. Her Frito-Lay smelling, no, munch Fritos go. Yeah, Fritos smelling pause. So pause the video and then start working out your problems, and then restart the video when either you get stuck or you finished it, and check your answer real carefully. This is gonna help you learn this material really well. So today we'll finish up chapter 14, conjugated alkenes. Then we'll start chapter 15, aromaticity. So yep, everything's online as you saw, and I'll start telling you about the total synthesis. I've been busy with learning how to get these videos made and everything, so but we'll get going on those. And so at this point, I'm thinking most of you have already taken the conjugated diene hydrobromination quiz, and I hope it went well. If you're seeing this earlier than 11 a.m. on Wednesday, then you probably haven't taken the quiz yet. And so here's a little bit about that if you're seeing it early. Please let me know, well, after you take the quiz, if you have any challenges. This was like I was hoping this would be a good test to figure out how it all works. If you have not taken the quiz yet, you're reading this early, okay. Study and practice the quiz. And I have a PowerPoint file with the key and a blank quiz. I also have a video of me working through that animated PowerPoint file. And they're both here in the mechanism quizzes area. And here it is, conjugated diene, key animated. So you can download that PowerPoint file and click through it. And then this one is a video link, a YouTube link, where I talk through clicking through the slides. I'll email the quiz to everyone at 11 a.m. tomorrow, Wednesday the 18th. And use this emailed quiz, part of me testing this out. So I want to use that one that I emailed, not the one that's already online. And then handwrite out the answers and photo it or cam scan it and email it back to me within 30 minutes. Let's see if this is possible. This is a no threat quiz because it's 5 points extra credit. So, but I want you all to get the full 5 points. So study it and learn it. Do it. If you can't print it or don't want to, you can write it out on a blank piece of paper. And if you have a tablet, an iPad, or something like that, you can do it that way and send it to me. All right, so look for emails also about lab data to come soon. Just kind of triaging what's most important to get to you first, and that's I haven't got all that yet. Thanks. I'm very excited to announce our first ever virtual SOTW, or VSOTW. I don't know. I think I'm gonna go with virtual SOTW, and this one is very deserving. A golden eagle, the Deloro student, teaches swim lessons. No, it's not Kelly again. Favorite holiday is St. Patrick's Day. Perfect timing. Made Guinness brownies with creme de menthe frosting and corned beef and cabbage, of course. Is a certified EMT. Nope, it's not Vadim again. Favorite color is purple. Will be a pediatrician. Has a 6-week trip to Italy planned for this summer. I hope that works out. Great-grandfather was born in Italy and came to the U.S. to run the mafia. Woo. And has hosted 7 international students, so has foreign exchange sisters all around the world. And who is it? Nope, it's not Jeff again. It's Emily. Emily Banahan. Everyone, please give a warm Sierra College welcome to our new virtual SOTW Student of the Week, Emily Banahan. I thought I'd start the lecture off with another example of this conjugated diene hydrobromination, in which temperature will decide whether it's under kinetic control or thermodynamic control. And so I thought it'd be cool. I gave you the exact same question the students last year got. So this was a question on their exam. You could probably expect something like this on your next exam. And so here's the question. at 0 degrees Celsius, what's the major product at product or products? And then at 40 degrees Celsius, under heat conditions, what's the major product or products? Is it under kinetic or thermo here? Kinetic or thermo, and then we got the mechanism, and then energy versus reaction coordinate diagram. And I don't want to spend a lot of time on this, but I want to give you a chance to try it and look it over. So here is the answer key. And you'll see in the question I did say they didn't have to draw the transition states because it kind of got crowded, but I gave them to you anyhow. The main concepts here are that you initially form the tertiary allylic carbocation. That's the most stable, so it has resonance. You wouldn't want to make a primary carbocation here or there. You want to make the tertiary allylic. And then the bromide attacks. The primary carbocation has less steric hindrance, but the bromide is polarizable to single atom. It is a big atom, but that makes it polarizable. So this is a little bit slower, but it results in a lower energy product. Whereas the tertiary carbon radical, it's a faster reaction because if you consider the resonance hybrid, we believe the tertiary spot is more positive, and so the bromide is more attracted to it. And even though there's steric hindrance there, that extra positive charge draws it there. So that's a faster reaction, but it's a higher energy product. So if we run it at cool conditions, 0 degrees Celsius, you get the tertiary bromide because it's faster and the reactions aren't reversible, so it's under kinetic control. And then if you heat it up, you get the thermodynamically controlled reaction, which gives you the tetrasubstituted alkene, and it's a little bit slower, but once it's formed, the reaction is reversible, but not as reversible as these products. So here's the reaction coordinate diagram. Check it out, try to work it out, and see how you do. Next up is the Diels-Alder mechanism reaction. This is outcome 9. And the Diels-Alder reaction, it's a big one. The two scientists, Diels and Alder, got the Nobel Prize for it. And it involves making a 6-membered ring. And remember, 6-membered rings are very important. We did our chair confirmations and all that. So here we go. This is the simplest Diels-Alder reaction. So we have a diene and it's going to react with an alkene. And we refer to the alkene as the dienophile. Makes sense. It loves dienes that react. And here's how they react. I'm going to number around the ring like this. 1, 2, 3, 4, 6. Not a ring yet, but and imagine a hinge at carbon 1 and this pi bond swinging out to make a bond between 1 and 6, and then a hinge at 5 and that pi bond swinging out to make a bond between 5 and 4, and finally a hinge at 3 to make a bond between pi bond between 3 and 2. Very similar to the electrocyclic reactions we were doing, except in this case we make a 6-membered ring, and we've got 1, 2, 3, 4, 5, 6. You make a cyclohexene. Usually, always you make a cyclohexene. You can make other things too. We'll see examples of that. Most often cyclohexene. And this is a big deal because you got a 6-membered ring. You can hydrogenate that if you want to make a cycloalkane. You can have different groups on your diene and on your dienophile, and that's what we're going to do. We're going to do some examples like that. Let's try, one other thing. Usually these require heat. They might use a solvent that has a higher boiling point. Let's say we use toluene in this one, because toluene's got a boiling point of about 110 degrees Celsius. So if you boil it in toluene, reflux it, it might react for you. If that's not hot enough, you could use a heavier solvent, maybe xylenes. So remember, we have our orthoxylene. metaxylene, and then our paraxylenes. And usually you'll buy a mixture of all three, and we refer to the mix as xylenes, and I like to draw like the third, just the methyl off the middle, saying it's a mixture of ortho, meta, para. So this one's boiling point's about 140. So if it's not hot enough, 110, you can heat it up higher, 140, get the things to react. Okay, so now let's look at something else even more impressive about this reaction. It is the stereochem. This particular example had no stereochem. But if we have different groups out here, we'll have stereochemistry in the product. So let's, first we'll focus on the dienophile. That's a little easier. So let's look at an example like this. So for this reaction, we have our diene, just a simple 1,3-butadiene. Oh, and it has to be in what conformation there? That's not a double bond, not a full double bond, but a partial double bond, right? Remember? So this one, is it S-cis or S-trans? S-cis. For the Diels-Alder reaction to react, you need S-cis. So the S-trans, you can see these two carbons are too far away to react with the dienophile. So this, which do you think is lower in energy, the S-cis or the S-trans? I'd say the S-trans, so you can see why maybe you need heat to get into that higher energy conformation. So you got your diene, now you have your dienophile. Let's draw out the curved arrow mechanism and just look at the regio product first, and then the regiochem, and then we'll look at the stereochem. So we can number it the same: 1, 2, 3, 4, 5, 6. And I'll show the hinge again here, hinge here, hinge there. Let's say we're heating this up in xylenes again. And we will get, again, cyclohexene. And I'll just draw the regiochemistry at first. So now number it. And then, okay, this is the regiochemistry. Okay, so how do we determine the stereochemistry? Well, it turns out on your dienophile, if your groups are cis on the dienophile, they'll be cis on the product side. So the dienophile, cis to cis products. And that seems reasonable. That one's kind of easy to see. So what that means is when I add the stereochem, I should have something like this. I can draw it wedged. Like that, and, or I could have drawn it dash dash, but I wouldn't draw both because this is meso, and if I said plus the dash dash molecule, that implies I don't know what's going on. This has an internal plane of symmetry, it's meso. When you flip it over, it'll look exactly like that. It'll look dash dash. All right, so there's one dienophile with some stereochem. And now let's try some more. pause the video, try to draw the curvature mechanism, the regiochemical product, and then what you think the stereochem should be. Did you pause it? Okay, now you did. Now we're back. So let's work this out. This particular molecule is trapped in the S-cis type of conformation and can't go S-trans. More reactive, I predict, than that one. Put my hinge here. Put my hinge here. Hinge there. So there's my regiochemistry. I've got two stereocenters, carbons 5 and 6, and now I just need to think about stereochemistry. So my dienophile is trans. So what do you guess the products are going to be? Trans. Easy. Not too bad, huh? So my final product is and then I make that product, and I randomly chose to go wedge on top, dash on the bottom. But what if I did the other way? Did it the other way? Would it be a different molecule? Let's draw it out and look at it. So, are they the same? Are they different? Let's do this. Let's think of this guy as having an aldehyde back away from us. I'll represent that with a pen right here. And then this one with the aldehyde coming at you, I have that represented with a pen. If I flip it over, is it going to look like that one? Are they going to be the same molecule? When I flip it over, the upper one's pointing at you. Flip it over, the upper one's still pointing at you. It won't overlap. These are different molecules, and you'll get their enantiomers, so it's a racemic mixture of enantiomers in this case. And if you want, you can confirm what's there with the absolute configuration. So A, B, C, this one's going to be R. A, B, C, but we're looking at the wrong side. This is the pirate one, R, R. And then this one is, let me double check, A, B, C, S. And this one's A, B, C, yep. So that one's left-handed, sinister, because left-handed people are different, and different is wrong. So racemic mixture of enantiomers, we got that one done. I'm going to pause here. Okay, now we saw when the dienophile was cis. Your product was cis. And then when the dienophile was trans, the product was trans. And that particular one we got enantiomers. maybe you always get an enantiomers. Pretty sure. This one you won't always get just one product though. X's are different molecules, different groups. Okay, so we got dienophiles. Cis dienophile gives you cis products. Trans dienophile gives you trans product. So that's pretty easy. The diene is not much more difficult. Let's look at an example. I'll do this one here, put a couple methyls on that one, and just go with the ethylene as my dienophile. So on this guy, we've got a diene. For the diene stereochemistry, if your groups are pointing out, then there'll be cis in the products. If they're pointing in, there'll be cis in the products. So if you have, I think of it as like, if it's out, out, and out, you get a cis arrangement of those two groups. And if they're in and in, you also get a cis arrangement. And then I'm sure you can infer if you have one out and one in, that's when it comes out trans. So let's do this one and see. I'll number again. 1, 2, 3, 4, 6. See the hinge here. Hinge there. Chem. First. I made 2 stereocenters there. And now I just need to add on the stereochem. The 2 methyls were both pointing out. Oh, by the way, this is like pointing out, and that's pointing in. Hope you were getting what I was saying there. There we go. So they're both cis. All right, let's do some more examples. Oh, here. Box this up. Okay, let's look at this one. On this one, I'm using bromobenzene as a solvent. That's a good high boiling point solvent too. I have my diene here, and both of its groups that aren't hydrogens are both pointing in. This one's an in and in one. And I don't know if I explained it that great last time. Let me say this. This is what I'm thinking of as out and out on a diene, and this is in and in. And then my dienophile it is cis. The 2 groups are cis and they're actually attached to each other. So pause the video, draw the curved arrow mechanism, the regiochemistry, then add the stereochemistry, and come back. Did you pause? Got to pause. Here we go. 1, 2, 3, 4, 6. These arrows are kind of nice. I like these cyclic reactions. And the product's easy to draw if you just kind of start with the cyclohexene. If you have your diene over on this side. And then I can start numbering now too. So 1, 2, 3, 4, 5, 6. And then off of carbon 1, I have an ethyl. Off of carbon 4, I have an ethyl. 5 and 6 connect together in what is referred to as an anhydride. Okay, so that's our regiochem. When you're first practicing these, do the regiochem first, then do the stereochem. After a while, you can skip drawing the regiochem product. Oh, and we're going to add stereochem. This guy has 1, 2, 3, 4 stereocenters. So let's start putting it together. So the ethyls, they were both inside. So when they're both in and in, then they should be cis on the product, right? So let's start with, say, wedge. I got wedgie, wedgie. Boom, there we go. And then the dienophile was cis. So it should be cis here. I'll go ahead and make it wedge too. Wedge, wedge, connect oxygen. And there's one product with its stereochemistry. Now I have to start trying to think about, could other products have formed? Could I get another stereoisomer to this? And what do you think? Think we can get another stereoisomer? Yes, we can. So we could also have, say I keep the ethyls wedged, then my anhydride can be dashed. Because I'm still following my rules of the dienes in gave me, they're still cis to each other. And then the dienophile, it started off cis, so it should be a cis product. And that's cis as well. And these are different. Should I draw up something like this? Should I say, oh, this is another one. A dash, 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 all dash. Should I draw that as if it's a different product, a new, unique product? No. This is just the all wedge flipped over. So if you draw this one, then you're like showing you don't understand stereochem well enough, and that's not good. So don't draw that one. What about this other one? Can we draw, or should we draw the ethyls dashed and the anhydride wedge? Should we do that? Is that a different, unique molecule? No. You just flip it over. Oh wow. It looks like it's unique because I left off a methyl there. Yeah, you just flip it over and it's the same thing. So don't draw that one either. This one, we just have those two products. And how are they related? They're diastereomers. They're diastereomers because they're not mirror images, but they have the same molecular formula, same connectivity. Okay, and if you work out their conjugal prelog R and S, you can see that they're not all completely opposite of each other. We do not get an equal mixture of them either. For these ones, it's a bit of a process to figure out which one's major, so I'm not going to ask it. I just wanted to draw them both. Another thing, they're both meso. They both have a plane of symmetry. So this is a meso compound, and this is a meso. All right, so that one's pretty tricky. Not super tricky, but you can see if you don't have symmetry here and here, whew, you can get a whole bunch of products. And when I first taught Diels-Alder, I used to go into how to find every product possible and predict the major ones. And it was, just took too long. It was like a whole lecture, and I realized it's more of a graduate level type of thing. So I'm gonna give you more straightforward ones like this. But so far, these are still just the beginning. We're gonna do these other Diels-Alders now that gives you bicyclic compounds. Okay, now we're gonna do Diels-Alder reactions that result in these bicyclic compounds. And you'll see what that means, and we're gonna learn how to draw them. It's like when we learned how to draw cyclohexane chair conformations, but it's easier than the chair conformations. At first, it might seem like it's not, but it is. So here's an example. If I have a diene like this, so my diene the diene is in a ring, some interesting things happen. And then here's my dienophile. The diene in the ring here, it's two groups. How would you describe them? Are they both pointing in, both pointing out, or one in, one out? They're in and in. And so this is in, that's in. And then, so we're going to get a cis product in terms of those groups. All right, let's number it. 1, 2, 3, 4. Same mechanism as before. There we go. So we got to avoid that ring here. I'm going to go ahead and label these A and B. Let's see what we get. Okay, that might look a little weird. Let me put some letters and numbers on it so you see what's going on. So this is carbon 1, 2, 3, 4, 5, 6, just like we had before. But we also have carbons A and B, which form what we're going to term as a bridge. So A and B are attached to 1 and 4. They're still attached to 1 and 4. And so this is the, think of this as your first regio. And then we're going to draw it with stereochem, but not quite, that won't be the final drawing. So I'm going to say add stereochem, and I'm going to say in 2 dimensionals, 2D. So these, this bridge carbons A and B, should they be cis or trans? Well, they're both pointing in, they're going to be cis. I can start off with calling them wedge. Let's say wedge, and then they go across there. So let me make sure we got all the numbers and letters. 1, 2, 3, 4, 5, 6, A and B. Okay, so we got the regiochem correct, and the stereochem in 2 dimensions. But that's not the final answer. We want to be able to draw this in 3 dimensions. So let's add the 3D. And this is how we'll draw them. With a little practice, they're not too hard to draw, and I want you to practice. I'm going to make you good at it. It looks like this. You kind of, I like to start it with carbon 2, and then I draw down to 3 at an angle, to 4, and then I draw my bridge. A, B, 1, 6, 5, and across. And then I draw the bond between 2 and 6, and I disconnect right there. It's not, the bond's not broken, it's just meant to give you 3-dimensional depth, so where you can see that's behind. Let me start numbering things so it makes a lot more sense. That's where my alkene is too. So we've got 1, 2, 3, 4, 5, 4, 5, 6, and this is A, and that's B. So what I just did was I took the ring that was flat on the board, like this, kind of flat on the board, and I went this way with it. So if I had, say my ring, it's got a bridge and it's coming out. It's got a bridge and it's coming out at you right here, right? So the bridge is coming out at you, A, that's our A and B. And I go like that, and now they're pointing up. Okay, so this one, if I draw the bridge as dash dash, the bridge can be drawn downward, but it's the same molecule, it's meso, so you just get that one product. But let's practice drawing that. So this is the bicyclic compound. And we refer to A and B as a bridge. So this bicyclic compound has a 2-carbon bridge. In this case, 5 and 6 could also be the bridge. But this is the way we're going to think about it and draw it. So let's practice that. I'll show you how to do it. Okay. So as I showed you before, I start with 2 to 3, and I draw them at an angle. So I go down, and then I go from 3 to 4, then I go bridge. Sometimes they look better than others. So there it is. And then I draw my pi bond in there, and I got it. So why don't you pause the video? Pause. Ryan, did you pause? Pause, Ryan. Okay. Okay, now Ryan's pause, let's talk about it. Just kidding. All right, so now try to draw it, and then here I'll draw some more. Let's see if we can helps to see more than once. Okay, down, over. I don't like that one as much. That's a little better. Oh, that's pretty good, huh? It looks sort of like Clifford the dog. Let's do it again. There we go. Okay, so now we're going to try some other ones. Let's try one with a, instead of a 2-carbon bridge, a 1-carbon bridge. And we'll add some groups to the dienophile. Okay, so we're back. I got another one here. This one's getting a little bit more complicated, but you'll see, it's totally doable. We have our diene, and it has its 2 groups, both inside, both outside, or 1 in, 1 out. Both in and in. So that's going to give us the cis. And this one's groups are attached, it's in a ring, so it's going to be bicyclic. Okay, and then our dienophile, this one has cis groups, the 2 esters, and so they're going to give cis products. So let's draw out the mechanism. 1, 2, 3, 4, 5, 6. And I think I've always been starting with like carbon, the pi bond between 1 and 2 swinging open, but you could start also with 3 and 4 swinging that way. It's the same thing. All right, so let's do our regio product first. And I'm going to call this one carbon bridge here A. And I'll put that A right there. Okay, so there it is in just the regiochemistry. So let's add stereochemistry in 2 dimensions first. Since A, they're both inside, so be cis, I'll go ahead and wedge it. So that's A. 1, 2, 3, 4, 5, 6. Okay. And then on the carbons 6 and 5 of the dienophile, they're cis, so they need to be cis. So if I go wedge here, and wedge here, that would be cis. So in terms of the 2 dimensions, is that the only product you think you can get? You have to have the A be cis, but I mean it's attached, it's obvious. And then these 2 esters have to be cis. Is there another arrangement that I can have? Yes. I can also have this. And that's actually all that you can have. If I do all dashed, that's just this flipped over. If I went dashed here and wedged there, that's just the molecule flipped over. Okay, so I've got 2 molecules here. How are these related? Are they mirror images of each other? No, but they have the same molecular formula, same connectivity. So these are diastereomers. And they are not produced in the same amount. And for these ones, I will have you know which is the major product. Okay, but first let's draw them in 3D. So I'm starting off the same. I guess I added pi 1 right from the start. Go down like that, and then I come over. This is carbons 2 to 3 to 4. And if you remember, for the other ones, I went from 2 to 3 to 4, and then I went to my bridge. I'm going to do the same here. I'm going to go up to A, and then just down right away. So you see how I just have a 1 carbon bridge when I do it that way? So I've got 1, 2, 3, 4, 5, 6, and I've got my bridge A there. And then on the 5 and 6, we're going to draw these like the following way, like 1 up and 1 down. And what do you think at carbon 6? Do you think that ester is pointing up or down? Guess. So A is wedged, the ester is wedged, A is up, ester's up. And then that's the hydrogen there. There was a hydrogen right here. And there it is there. Okay, And you can visualize it if you see, this is the ring in the board. My ester is pointing towards you, and this ester is pointing towards you. When I go like that, they'll both be pointing up, right? So the esters are coming at you, and now they're pointing up. So now I'll draw the other one here. It gets a little cramped on these, just do your best. But make sure you can tell the reader that they're both going up. When you draw your bridge up and your groups besides hydrogen pointing up, we call this product the exo product. So that's the exo. Let's look at the next one. So again, I start with 2 to 3, come over to 4, up to A, down. There we go. And then for 5 and 6, I'm going to have this time the esters point down. Because as you can see, the esters are pointing the opposite direction of the bridge A. So then you'd be pointing the opposite way too. Turns out this one we call the endo product. And the endo product is normally always the major product. So I want you to be able to draw these in 3D and know that the endo is major. When I was first teaching this, I think it was maybe like my first or second year, might be my first year, and I was like, yeah, the endo product's major, and then some of the students started laughing, oh yeah, endo's major. And I kind of laughed along, but I didn't know what they were talking about. And then I was like, wait, what are you talking about? I guess they were talking about like marijuana grown indoor endo. Wasn't listening close enough to Snoop Dogg. But yeah, that's the endo product, not related to the legalization in California. Okay, here's another nice one. I want you to, I'm going to talk about it, and I want you to pause the video and try to do it. So for this one, we have on the diene an in and in, and it's going to be a bicyclic one. And then this one, our dienophile, it's cis, so it's going to be cis. And then we know from bicyclic it should be, we should get an endo and an exo product, and the endo will be the major product. Oh, before I let you go to try it, let me show you just for a 2-carbon bridge system like this, the endo exo. Make sure you got that part down. So this up here is exo, down here is endo. Exo, endo. So use that to guide you to see what's the major product. Okay, so pause, try to do it. Ryan, put the donut down. Pause. We'll wipe your finger off, don't get your keyboard all sticky. Pause, and then do it. All right, so back at it. I'm gonna do the curved arrow mechanism again. Got my 1, 2, 3, 4, 5, 6, an A and a B. I'm gonna go quick on this one. If you're not so good, don't skip the steps like I am. But if you're getting the hang of it, you can start skipping the steps. Here it is. Boom. And I have methyls off of here and alkene there. So what do I have? I've got 1, 2, 3, 4, 5, 6. And then always draw in the hydrogens. I normally don't I tell you not to draw hydrogens except for on aldehydes. But I want to draw them here so it's clear that this is what, the indo or the exo? Indo. And this is the major product. And this is your A and B. 2 carbon bridge. And now I'll draw the minor product, the exo. So I say plus. It's looking a little ugly this time. Yeah, I don't like it. It's okay. Use pencils or get yourself some awesome Japanese friction erasable pens. Ask Amanda. Here we go. Bam. Now this one's a little weirder to draw, but we'll just do our best. Maybe I'll go something like that, and then I'm going to draw in this H down. And man, I made it too small. There we go. And that one would be the exo product. And that's the minor. It's exo because the 2 non-hydrogen groups are pointing upward. Okay, why is indo major? Why is exo minor? It's the last I checked, it's up for debate. It could be steric hindrance. It could be an overlap of the pi bond here with the bonding that's forming in the reaction. So I won't ask you why indo's major, but I want you to know indo's major. That's like a common thing you'll find, like an MCAT, a GRE. So you'll be expected to know that. Okay, so just practice those. That's the key. Okay. We're almost done with chapter 14, except for we gotta do some retros, right? But this one's a good one, and hopefully when you look at it, you're gonna see a cycloalkene. A cyclohexene. And when you see cyclohexene, think Diels alder. I'll pretty much for sure put Diels alder containing retro on the next exam too. I always like these ones. And a little practice, you'll get them. You guys are smart. And we got some alkynes. We have to consider, we've got, looks like these guys are cis, huh? From the diene. And also cis from the dienophile. So, retro. Oh. Before I do it, I want you to try. So pause it, okay? Brian? Put down the hot dog. Pause. Yep. Wipe the mustard off your hand. Come on, you're gonna get your keyboard over. So pause it. Try it out. If you get stuck, that's okay. Play. Get going. And once you get, if you're playing it, if you're watching me do it, and you get past whatever was making you get stuck, pause again. Try to finish it. Okay, here we go. So. Got this cyclohexene, which is screaming Diels alder to me. So I'm going to draw one of them and say plus diastereomer. These two are diastereomers, yep. And now, what am I gonna do? I remember when I was doing the mechanisms, I kept numbering the ring this way: 1, 2, 3, 4, 5, 6. And if you remember, the bonds were formed between 1 and 6, and 4 and 5. You can actually even kind of see a reverse Diels-Alder, which is a reaction that occurs like that. So our first retro step back is to make our diene and dienophile. And our diene has 2 ethyls that are cis, so I can either have them both be out or in. So either one of those dienes will work fine for this. And then my dienophile has 2 methyl cis and deuterium cis, so I need like a methyl, a deuterium, and a deuterium. And you can see already how you can get either of these from the alkyne, I hope. So this can come from, well, the dialkyne. If I want to do this, I would use the dissolving metal reduction with sodium metal, the rest, to give me the trans alkene. Or it can come from this one via the Lindlar's catalyst. Okay, so that one's not too bad. The other ones, the dienophile is going to take a little more work, but not too much. This can come from an alkyne with D2 and Lindlar's catalyst, right? And then the alkyne can come from the dibromide. I'll leave off the stereochem for now. I'll add it later. Which can come from the alkene, and it can come from the mixture of cis and trans alkene, which can come from the bromide, secondary bromide, which can come from butane, which we need to start from. So there's our retro. Let's do the synthesis. Okay, here's our synthesis. I'll start with the dienophile. So if I first add bromine and light, that'll give me the secondary bromide. And then if I follow that up with a big base or a small base, I want the internal alkene, small base. Sodium methoxide, methanol. I'll get both the trans and the cis alkene, which I can represent with the wiggle. Then these guys, I'll add the Br2, carbon tetrachloride. When I do that, the trans alkene will give me a meso compound. I know that doesn't look meso there, but when you rotate around the bond, you'll see it is meso. And then the cis alkene will give me the enantiomers. And I can represent all those with actually a wiggle wiggle this case. All of those equal that one, all of the possible combinations. Okay, and having this mixture is fine because we're going to next make the alkyne with sodium amide and liquid ammonia and follow it up with an aqueous workup to quench, well, you don't need to, it's not a terminal alkyne, you're not quenching the alkyne, but it'll quench the excess sodium amide. And I will get my internal alkyne. Then I need to create a cis alkene with deuteriums. So I want to do a partial reduction of this, so I'll add D2 gas and Lindlar's catalyst. And there we go, I got my dinophile. Now to make the diene, easy enough. I just need to do a partial reduction of both of the alkynes. And I can do it actually this to make this the anti-addition or the syn addition. Since I already did syn addition, why don't I do anti? So I'll add 1A sodium metal in liquid ammonia and follow that up with water. And this will give me the following. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. All right, looks right. And I'm set up to add my dinophile. And maybe I'll do this in xylenes. Oh, you know what? I've been using this symbol today, but I keep forgetting to remind you what that means. That means reflux. So we're heating the reaction to its refluxing. All right, and our product should be cyclohexene. Both of the ethyls are out, so I can draw them as wedge, wedge. And then my dinophile, the methyls are cis, so I can draw them wedged, and then the deuteriums would be dashed. And then, of course, I have the diastereomer. Wedged out deuteriums, methyl back. And there you have it. Not too bad, huh? Okay, I'm back. I got another retro. This one involves a bicyclic. So I know this is a lot, but as you practice, you get it. My students do really well in this in the past. So let's start with our retro. So it looks like this is the indo or the exo product. Wait, there's the ester. That's indo, right? That would make sense. That's if we want the major product in this retro, we'll go with indo. So I'm not even having to draw the exo, it's a minor product. Okay, so for the retro, remember, I numbered these as 1, 2, 3, 4, 5, 6. And then I had my fridges as A and B. And the bonds that were made were between 1 and 6 and 4 and 5. But there's something else about this one. I can't disconnect that just yet. Do you see what's happening there? 2 and 3 should have an alkene. So it looks like that alkene was reduced at the end. Okay, yeah, I can see. You can reduce alkenes, hydrogen gas, palladium on carbon. Now I can disconnect here. Let's go back to my numbering. 1, 2, 3, 4, 5, 6. A, B. And imagine the mechanism backwards. You could see a hinge on 1. This pi bond going to form between 1 and 2. Hinge on 3. Pi bond between 3 and 4, and then the bond here breaks, becomes a pi bond there. This was carbon 1, carbon 2, carbon 3, 4, 5, 6, and this was A and B. It's looking good. And I was given the diene file, so that's ready to go. That's done. But now I need to make the diene, or show how the diene was made. So I can see this coming from an allylic bromide. Do you see an E2 happening there? I like it. And wait, allylic bromide. How do we make those? Oh yeah, that's just a from the alkene with NBS, N-bromosuccinimide. Remember, it creates a low concentration of bromine, and light will radicalize that bromine. Prefers to make the allylic radical on either side, and it would be the same. And now this alkene can come from just a bromide. No stereocenter there. That's from the cyclohexane. This one's actually kind of short. Okay, I'll make the diene first. Take my cyclohexane, bromine and light, follow it up with a sterically hindered strong base. The size of the base does not matter because it's symmetric. And I get an alkene. Then I need to add a bromine allylic. This is an allylic carbon. And so is that one. They're symmetric. So I'll add my NBS, carbon tetrachloride, and a little light. So the NBS is not very soluble in carbon tetrachloride. It slowly dissolves, slowly makes a low concentration of bromine. Before the bromine can do anti-addition to the alkene, it gets hit with light to become a radical. And then it can make an allylic radical with a lower in energy because of resonance. And that leads to our allylic bromination. And it creates a stereocenter in this case. And then we could just add another big sterically hindered strong base. To do the E2. Boom, got our diene. And now we just add our diene file, which we were given. Heat it up, reflux it in bromobenzene. And we will get our endo product as a major product. We're almost done, so this is the endo major. Just gotta reduce that alkene. And I'll just say target molecule. Done. Whew. Okay, that's the end of chapter 14. But there's one dissolver I didn't show you yet. Let me show you one more. What do you think you get with a diene and a alkyne? Diene-O-5. They actually react well. If I number around the ring, you'll see I can go like this if I want. And the products are actually easier to deal with because there's less stereochemistry. Because these 5 and 6 here, they're an alkyne turning into an alkene. 5 and 6 have no stereo centers, but 1 and 4 do, but I didn't have anything on them initially. But I just want to make sure I forgot to mention those at the beginning. Just thought of them as I was doing the retro. All right, now I'm off to spend a few hours editing and finalizing this video and posting it. Put it up for you guys. All right, see you tomorrow.